So what kind of storage do you really need for Elasticsearch? Today we're going to take a deeper look and answer exactly that question. Hey everybody, I'm Rob Cowart, and today I want to talk to you about storage. Now, some of you out there probably know me as the creator of Elastaflow. So Elastaflow is a solution that I share on GitHub, and it's built upon the Elastic Stack. The Elastic Stack is Elasticsearch, Kibana, and Logstash. And some people sometimes call that ELK. And the purpose of Elastaflow is to allow you to easily leverage the Elastic Stack to collect and analyze network flow data. Network flow data is really a type of metadata about connections across the network. So it's which systems are talking to which other systems over which protocols and things of that nature. So that type of data is typically sent across the network using technologies like SFlow, NetFlow, IPFix. And it's a topic that I can go into a lot more detail on in a future video. However, that solution has really led to users coming to me and asking a lot of questions about the Elastic Stack. When I first created that solution, my assumption was that most of the users were going to be Elastic Stack users, and they would already know how to set up, install, and leverage the Elastic Stack. What really surprised me is that many users come to the Elastaflow solution because they're just looking for a better way to handle their flow data. And they really don't know a lot about the Elastic Stack. And so I get a lot of questions, and a lot of the issues that people open on that project have to do with questions around Elastic. And at some point, because flow data can be really high volume, at some point, there's also questions about how much resources do I need, what type of servers, and ultimately what type of storage. And that's really what this video is going to get to the heart of. Because ultimately what you need something that's going to provide the performance that's going to enable you to ingest data into Elasticsearch, as well as support all of the queries that users are going to have against that data. So it's kind of two parts that really need to be considered. I'm really going to focus on this particular video on ingest performance. Typically, especially when we're talking flow data or log analytics type use cases, the bulk of the performance requirement has to do with the ingestion of data. And querying is a little bit less of an issue. So, there's going to be some tests. We're going to look at some, I don't want to call them benchmarks really, but some real world ingestion of sample data to really understand how different types of storage can affect the performance of your Elasticsearch implementation. So yeah, we're going to look at a few different types of drives. Ultimately, it's kind of strange, actually. A lot of people don't realize that the Elastic Stack, specifically Elasticsearch, was really designed to leverage commodity hardware to scale out horizontally. That means multiple servers, multiple instances, and it achieves its scale by adding lots of servers. Now, ultimately what happens is I'll have users that come to me and they say, well, we have this one super server. Oh, I have 40 cores. Now, typically they mean they have like 28 cores, and there's hyper-threading. That's another topic. But they feel like they have lots of CPU, lots of cores, 256 gig of RAM. Oh yeah, and some RAID 5 hard disk, right? And they're wondering why performance is slow. And that's really the reason I want to dig in, provide some real data, and help everyone understand how the storage configuration, your choice of drives, can affect the performance of not only Elasticsearch, really any real-time data platform that you might be working with. So what I first want to do is explain how we're going to set up the test. I'm going to go on over to the Lightboard and we'll kind of diagram this out for you. So in order to perform our testing, we're going to need some data. Now, here in our lab environment, we have a lot of data that's coming in live from a number of different sources, flow data, firewall logs, that type of information, that currently all is ingested first into Kafka. And from Kafka, we send that data out to multiple different systems. So we're going to leverage this data that we already have available in our Kafka system. So as I mentioned, in the lab, we have a Kafka cluster. That Kafka cluster is made up of multiple nodes, and we're going to leverage the data from this to do our testing. So the first thing we're going to need to do is get some data out. So we're going to set up, also for the sake of our testing, a second Kafka instance. This is actually just going to be a single node cluster, just a single broker. We will export data out of Kafka. It's going to end up being, in this case, about 5.1 million records. So not sure exactly how many gigabytes that is, but it's going to be about 5.1 million records. That will be in JSON formatted data. So ultimately what we want to do is we want to get that data over into our Elasticsearch node. So for the Elasticsearch node, we're going to have multiple types of storage. We're going to have that NVMe drive. We're going to have those Sata hard drives. And we're also going to use the Sata SSDs that we have available. In particular, the two Sata setups, we're going to have two different types. One will be a single drive, and one will be a RAID 0. The same goes for the SSDs, a single drive and also a RAID 0. This one will be ×2, and this one will be actually a RAID 0 ×4. We're really trying to give those hard drives as much potential for performance as possible, because without a doubt our hypothesis is that's going to by far be the slowest type of data that we have available. Now, to get data from Kafka into our Elasticsearch instance, we actually have data in Kafka using 4 partitions in the topic that we will be reading from. And so we're going to leverage 2 instances. In this case, we're going to use Logstash. So these will be running on separate systems. They will read each from 2. It'll end up being 2 partitions each. That's just the automatic balancing action that happens from Kafka consumers. These will be in what's called a consumer group in Kafka. So they will be functioning as one virtual instance. And they will then be writing that data into Elasticsearch. So we're going to run this test multiple times. We're going to run on the NVMe. We're going to run on the individual hard drives and SSDs. And then we're also going to set those up in a RAID 0x4 for the hard drives, a RAID 0x2 for the SSDs. So that's going to be the test environment. This will allow us to, having that data coming out of Kafka, we're always going to have those 5.1 million instances. In between tests, we will reset the offsets of that Kafka topic so that we're always constantly starting at the beginning of data and reading the entire data set through for the test. It's going to give us really reproducible results. And since we're taking that original data from this live Kafka cluster, we have a really good I'll say variation of data, very real world, right? Synthetic benchmarks can oftentimes give you pretty confusing and not always real world results. But since we're leveraging real world data to start with, and we have it in a reproducible format, reading out of this particular Kafka topic, we should have be able to produce consistent results and give us some direct comparisons on which storage has which advantages over the other. Just to reiterate again what we just covered over on the Lightboard, we're going to be testing 3 types of storage systems. I have a few different drives. I have a NVMe drive from Samsung that we're going to be using for the test. This particular drive, I mean, this is an MLC-based drive, uses really pretty much most people consider about the best drive you can get outside of true enterprise class SSDs. So this is going to represent our most modern type of drive we're going to use. Then I also have some normal SSDs. Now these are Intel, the Skull Candy or whatever they used to call these things, right? Pretty good drives, SATA SSDs. So, not leveraging the PCI technology like an NVMe drive is going to do, but they do represent what's really the better end or the better performing SATA-based drives. Also a MLC type drive, so you expect to have a bit better write performance than some of the other options that you have available today. And of course, not exactly this one right here. This is kind of a really neat looking former show drive. But we're going to leverage some spinning SATA disk as well. And we have multiple of those as well because it's important to also not only test things as individual drives, but typically in a server, you're going to have an array of hard drives, array of storage media. And so we want to be able to test in the most optimum form. Now, when we do these tests, we're doing RAID 0, as I mentioned when I explained how the test was going to be set up. And we do that so that we can stripe across multiple drives in parallel to increase the overall performance of the storage. Now, there are other RAID configurations. I'm not going to talk at all about RAID 5 and RAID 6 because there are some well-documented, you can Google it, search it on the internet, there's some well-documented write penalty for using those technologies. I'm also not even going to talk about RAID 10, although if I was going to have redundancy in my storage, which is certainly something you should do if you're trying to do everything on a single node, you really should use RAID 10 because it is going to give you the best write performance. There is a little bit of a write penalty when because you do have the mirrored drive, so you have to write everything twice, and it has to verify that that was written properly to both drives. So it's not, you don't really get, if you go say from 4 drives to 8 drives, but there's mirroring involved, it's not, you really get more of the performance of 4 drives, not of a full 8, where a RAID 0 stripe will give you the performance across all of those. But when you do queries in a RAID 10, you should be able to read all those drives in parallel, including the mirrors, which typically is going to give you some better read performance. So that's what we're going to really focus on is just RAID 0, assuming that you on a single server would go to RAID 10, so you double the number of drives to have that redundancy. Now, many people will tell you with Elasticsearch and some of the other clustering type real-time data platforms that what you really should do is configure the storage for optimum performance. I definitely believe in this approach when you have a multi-node cluster, because the clustering itself is going to allow you to create multiple replicas of the data. And really those replicas are what's going to provide you redundancy. So I would always look to do something like creating a RAID 0 of the drives that I have available to me, striping across those for the best performance, and having multiple copies on additional servers in a multi-node cluster to give you redundancy. So again, that's another reason why we want to focus on RAID 0 in our tests. So we're going to have single drive NVMe, single drive spinning hard disk, single SATA SSD, and then we're going to do a 2-drive RAID 0 of the SATA SSDs, and a 4-drive, we want to try to give those hard drives every advantage they have, a 4-drive RAID 0 of the spinning hard disk. So those tests have been run. Let's go ahead and take a look at the results. While performing these tests, I used a different system to actually collect the metrics as the tests were running. Telegraph is the agent to collect the metrics. We're actually getting some metrics directly from the server where Elasticsearch is running. And that agent is also polling the REST API of Elasticsearch to collect the actual number of records or documents that are being ingested into the system. And that's what we see up here in the upper left. That's the chart we have. So the number of records being ingested. Wanted to also, though, understand where there might be bottlenecks in the system, confirm we're not hitting any other limits while doing the tests. So we're following CPU, both load and utilization, and we're looking at network traffic. I'm not going to talk too much about the network traffic. Trust me, across all of the tests, you'll notice that it was well below our maximum available bandwidth of 1 gigabit per second. In fact, about 250 megabits per second is about the highest that we see it hit. We're also looking at storage metrics as far as write IOPS and write bytes. Again, primarily focused on the testing on writes because we want, most of the workloads, whether it be network flow data or log data, it's going to be an ingest or write-centric type of load. And so we're really focused on those write metrics. Obviously, if you're pushing a system to 100% or really close to its limits on its ability to write data, there's not going to be very many IOPS available when users want to query that data. So obviously, this is an is a ideal scenario for ingest, but realistically, you're going to achieve numbers that are a bit below these for each of these storage types so that there's headroom available for queries. The first one we're looking at here, this is the Samsung 970 Pro NVMe SSD. I really expected this to be the big winner of the test. Here we look at amount of data ingested. We're probably sitting at about 11,000, 11,500 is our average events per second that were able to be ingested. We do sometimes peak up a little bit over 15,000, but a pretty healthy number actually. I think considering that the server that we're running on here is just 4 cores and 32 gig of RAM, I feel like these numbers are pretty good actually. Now, when we go down to the chart with the I/O wait time on it, we can see that there is a significant amount of time where the CPU could be doing work if it was not waiting on threads that are waiting on I/O to return. And so that's why I included both I/O wait and utilization on this chart, because I wanted to show what potential there was for more performance. So clearly here when we see this much I/O wait, clearly we are limited by the ability of storage to write the data and return that successful write. It happens to be at a little over 2,000 I/O operations per second. I know you're going to see, when you look in some of the marketing literature, you're going to see some much higher IOPS numbers, but those are typically on 4K writes. The writes we're doing here are a bit bigger than that, so they're going to take a little bit longer. They're on average around 48 to 64 K bytes, not 4K bytes. Also, it's a little bit different number of threads, different queue lengths, etc. So you're not going to see 100,000 IOPS. That's an unrealistic thing for the usage pattern of Elasticsearch. We can see that we're clearly I/O bound, but we're able to get a little over 11,000, 11 and a half, maybe 12,000 events per second on an average. Moving on from this NVMe drive to our Sata SSD. So this is again an Intel 730 480 gig Sata SSD. Pretty respected high performance drive in its day, considered definitely among the better SSDs available at the time that it was on sale. And I can certainly see that echoed in the results we have. In fact, these results is what we see over here on the left-hand side. These results look very much like the results we saw for the Samsung NVMe drive. Again, we're sitting there right about 11 and a half, maybe 12,000 events per second. We got a split here, very similar split or utilization of the CPU, as well as about the same amount of I/O wait. Even over here on the IOPS, it's very similar, a little over 2,000 IOPS. I mean, the similarity between the NVMe drive and the single Sata SSD are really surprising. I have to admit that I expected the Samsung drive to have a margin of victory here of maybe 40 to 50%, but that hasn't really played itself out in the raw numbers. Continuing on to our third and final single drive test, we have the single Sata hard drive. This is a 7,200 RPM hard drive, and I will admit I've done some testing a few years back using SAS drives versus Sata drives, and I will tell you that you'll generally see 40 to 50%, maybe even up to maybe a bit more, 60, 70% better performance on something like a 15,000 RPM SAS drive compared to a 7,200 RPM Sata drive. However, it's not going to be anything close to what the SSDs are. So that's the big message here is you can't get around the laws of physics. So while we were seeing 11, 12,000 events per second using the Sata drive or using the SSDs, here on the spinning hard drives, we're down probably, I'd call this average about 750 events per second. Obviously, only at 200, maybe a little under 200 IOPS, which really is pretty good for a Sata drive, 7,200 RPM Sata drive. I have to say I expected this would probably be down around 100 to 125 at best as kind of an average. Looks like that average is probably a bit higher than that, so that is surprising, I would say. But despite that, we're maxed out. We have massive I/O wait here. we're really maxed out at what the theoretical IOPS limits of the drive are. There'd be no way, even at 750 events per second, there's going to be no way that we could support any type of serious query load on top of what we're already see here. So, beyond just the absolute bare minimum, lab type implementation of Elasticsearch, a 1 terabyte SATA drive is just not going to get the job done for you. So, this is a pretty clear indication. I know we're still looking at single drives, but it's already a pretty clear indication that if you're thinking about using hard drives with Elasticsearch, certainly for active, sometimes called hot nodes, where data is actively being ingested and queried by multiple users, you do not want to be using hard drives. SSDs is definitely the way to go. If we add 3 drives to the single hard drive, the situation does get a little bit better. It doesn't scale 100% linearly across all 4 of the drives. We go from about 750 events per second. We get up to about 2,300 events per second. So about 3 times what we were seeing with the single drive. Our test still takes a lot longer to complete. You also see just how quickly those tests were completing with the SSDs. All of our charts on all the dashboards I'm showing you are over a 45-minute time period. So you can see we barely got finished within that 45-minute time period here with the RAID 0 array of 4 hard drives, where we were finished in about 10 minutes or so on the SSDs. So pretty significant difference. We do see more IOPS also from this particular array than we did from the single drive. That's to be expected, right? If each drive, say, doing about 120 to 150 IOPS, then in an overall, the array is going to be able to handle a bit more than that. I think we see that here in this scenario. However, again, when I look at this, I'm thinking, when I think of the different customers I've worked with, I have had a few customers that, had a pretty low load. We're talking about, 2,000 to 3,000 events per second, but the bulk of them, we're talking 15, 20, 25,000 events per second. This is flow data, firewall logs, server logs, application logs, that type of data, even including some organizations that were up over 200,000 events per second. So the very, very, very smallest use cases, I think with this RAID 0, you could maybe get away with using hard drives. But again, you're right at the limit. Any type of query load on top of this is going to present a real challenge. So again, you really have to think twice, except for the absolute smallest use cases. Think twice about using hard drives. SSDs is definitely going to give you a lot less headaches, a lot better performance, going to give your users a lot better experience. So finally, we come to the second of our RAID 0 tests. And really, I have to say, the real surprise of all the tests we've run. As I mentioned, I really thought that Samsung NVMe SSD was going to be the clear leader, the clear winner of, if you want to declare a winner, the clear winner of these tests. However, we saw before, comparing in the single drive comparison, that we got about the same results from the single SATA SSD that we were getting from the Samsung NVMe SSD. When we take 2 of those SATA drives and run them in RAID 0, we see another bump up as well. So where we were averaging about 11 to maybe 12,000 events per second with those single SSDs, we're probably getting closer to about 13, 14,000. You could see sometimes it was even inching up close to 20,000 events per second with RAID 0 SSDs. So this is pretty significant, I would say. I mean, it's clearly, again, not linear scaling, but we do get a healthy bump by doing a RAID 0. You also notice that where the single SSD test, we were showing about the same amount of I/O weight as we had CPU utilization. And here we're seeing a significant reduction compared to those other 2 tests in I/O weight. So the CPU utilization is overall higher. The CPU is free to do more work because the write jobs, the write requests are returning more quickly, and we can then index more data. So quite interesting here. Unexpected result, I would have to say. It would be very interesting to test 2 NVMe drives in a RAID 0. I actually do have 2 of that particular Samsung 970 Pro drive. Unfortunately, one of them is currently in active duty in one of the other systems in the lab, so I wasn't really ready to tear that system apart to perform that test. Maybe could be something to add to this result set sometime in the future, but it definitely shows that there is some clear advantage to using multiple drives, also if you're using SSDs. In fact, I would say that based off of these tests, if I had to give you a recommendation, I would tell you to consider using a RAID 0, or if you have everything on a single server, maybe a RAID 10 of multiple SATA or probably SAS enterprise type SSDs. So now that we've seen the results, as I mentioned earlier while we're reviewing the different charts and stuff, I have to say that I was surprised. I was really expecting that this NVMe SSD was going to really win the show, win the day, and it was going to be what provided the best performance. Really by far, I really expected to have a good, pretty good advantage, if not, 40, 50% better performance than any of the other setups. However, in the end, it turned out to be these 2 SATA SSDs running in RAID 0 that actually provided the best performance. Now, there's a lot of reasons why that could be, right? A lot of SSD manufacturers love to tout the sequential performance, right? You'll have like multiple gigabytes per second of performance that those drives can read and write. However, sequential loads like that are really just for single user, single process, single thread with like big file copies or things like that. They're really not necessarily going to reflect real world, especially multi-threaded, multi-tenant, random type workloads that you're going to see in something like we have here with the Elasticsearch testing that we were doing, or a lot of other real-time data type platforms. Now, in the case that we saw in the benchmarks, right, there was clearly a lot of writes that were backing up, right, to the drive, because we saw the I/O weight as the different writes would be backing up. The CPU is pausing and it's waiting to write that data. So we can assume that we have multiple things writing, because we're also writing to multiple Elasticsearch indexes, about 30 indexes or so that were being written to simultaneously. So that means multiple shards, multiple, which in the underlying file system is really multiple files that were being written to. And so we had a lot of places we were writing to. We had a lot of data being sent in. So we had high queue depths, but also high threading. And that particular workload, right, we're never going to see like those gigabyte per second times with just a handful of drives like this. However, it was quite surprising that to me anyway, that these SATA drives, although these were really good SATA drives in their day, it was surprising to me that they beat that NVMe drive. So I think that just kind of confirms again that while I'm not saying use commodity like hard drives, you're really better off by having multiple commodity type hardware when you're leveraging Elasticsearch. So of course, I also recognize that these are consumer type or prosumer type equipment. Obviously in servers, you're going to have a little bit different level of hardware, but the principles that were covered here still apply. So I would encourage you to think, one, what you should have learned from this is hard drives, spinning disks, this is a no-no, right? You're just not going to get the level of ingest and, more importantly, the level of read performance that your users are going to want to have a responsive, good user experience. You need to stick to SSD drives for your Elasticsearch use cases, maybe on like warm nodes or cold nodes as they're called, hot, warm, cold architecture. That's probably a topic for an entirely different video. However, you maybe could use those in those type of uses. However, you really, for the best performance, want to stick to SSDs as much as possible. So do those have to be the absolute most cutting edge? I mean, I would have loved to have tested something like Intel's Optane drives as part of this test. Unfortunately, don't have any of those expensive drives available to me. I would love for, say, Intel to donate something for some testing. That would be a pretty awesome test to conduct and add to this particular set of results. However, rest assured that you can very much just leverage an array of, say, I could imagine like 8 SATA or SAS type enterprise drives in a RAID 0 configuration. If you have a single server, okay, it could be a RAID 10 configuration to give you that redundancy, but certainly in some type of striped RAID configuration to allow you to leverage all those drives in parallel to their fullest is what's going to give you the best performance. So yeah, that's pretty much it. I hope you got something out of this video. If you are interested in videos like this, again, I'm really just getting started here with the channel, so please down below hit subscribe, give me a thumbs up that you like the video, and I look forward to bringing you more such content in the future. Thanks.